So next, we're going to hear from Patricia. So Patricia Leopold has been part of the of NIAX for over a decade and currently coordinates the climate change response framework in the Mid-Atlantic and Central Appalachian regions, where she works with a variety of partners to address vulnerabilities through adaptation planning. She received a BS in Fisheries and Wildlife from Michigan State University and her master's in forestry from Michigan Tech University.
Thank you, Maddie. So my presentation today will focus on climate change impacts on West Virginia forests. But as we just saw, climate change is just one of the many topics that forest managers are thinking about on a daily basis. Climate change can directly affect some of those topics like drought and extreme weather, and then it can indirectly affect some of our other topics that we're struggling with, non-native invasive species, pests and pathogens, for example. So Maddie already talked about the climate change response framework and the four main components that make up our eco-regional response to climate change. And this morning, I will be focusing on the vulnerability assessment and synthesis. So we've created vulnerability assessments for eco regions across the eastern US, really focusing on areas where there are cohesive partnerships of land managers and researchers that cover broad categories of fairly similar forest ecosystems. And so each of these reports really covers a different geography and a different partnership, and it's geared toward natural resource professionals with little to no background in climate change science. So these reports focus on tree species, forest ecosystem responses to past climate change, a range of potential future climate changes, and then they also incorporate species distribution models and process models like the Climate Change Tree Atlas, which we rely heavily on, and Landis Pro, which is a process model. And then we take all of that information and use it in an expert panel of researchers and managers in a formal process to assess the vulnerability of these major forest ecosystems in each region. And then an intentional limitation of these reports is that they provide a baseline of information on regional vulnerability, but then they stop short of providing any recommendations or judgments about what to do or how to use this information. And as Maddie mentioned, the answer to that question is actually provided in the forest adaptation resources, which we can dive into in a different session. And so for West Virginia is part of the Central Appalachians Vulnerability Assessment. And so it's covered with Ohio and also Eastern Maryland. And so today I'll be summarizing some of the information that is included in the Central Appalachians Vulnerability Assessment. This chart shows observed and projected changes in global average temperature under 4 emissions pathways. Each line represents a possible pathway based on assumptions about future greenhouse gas emissions, also social behavior, and national and international policy. The bars on the right show the likely ranges in temperature by the end of the century relative to the 1986 to 2005 average. So we can see that the light blue line here represents representative concentration pathway 4.5, a relatively low amount of change that would be driven by significantly reduced greenhouse gas emissions. And then the top red line represents RCP 8.5 and the highest amount of change. And this would be driven by steady increases in greenhouse gas emissions. And when we use these two RCP scenarios together, they can bracket most of the future emissions as outlined by the Intergovernmental Panel on Climate Change and their evaluation of emission scenarios. These emission scenarios are used by downscale climate models to then project climate change at regional or national scales, such as the United States or the Central Appalachians region. So here we present the data from two downscaled general climate models, the CCSM4 and the Hadley. And these models exhibit a wide range in sensitivity to carbon dioxide in the atmosphere. The CCSM4 model with the RCP 4.5 scenario, that combination represents the least amount of temperature change out of any of the model scenario combinations. And then the Hadley model together with the RCP 8.5 represents the most temperature change. And so together, these combinations really exhibit the full range of potential future climate change. So then if we zoom in on West Virginia at the end of the century, we can expect to see an increase of a little more than 4 degrees Fahrenheit. So 4.1 to 4.5 degrees Fahrenheit over most of West Virginia under the lower emissions scenario 4.5. And then we see maybe a little more warming even in this western part of West Virginia up to 7.6 degrees Fahrenheit by the end of the century. And then under the high emissions scenario, that change is more uniform across West Virginia, and we're looking at temperature increases of 11 to 12.4 degrees Fahrenheit. So really a large amount of change. And we can also look at projected temperature by season. So here we see winter in the top row and spring in the bottom row. And we see the low emissions scenario on the left-hand side and the high emissions scenario on the right-hand side. And the low emissions scenario projects significant warming across West Virginia in both seasons. So by up to 5 degrees in spring and then up to 7 degrees in winter. And then the high scenario projects even greater increases of up to 11 degrees, 9 degrees in spring, 9 to 10 degrees. And then up in Ohio, we're looking at 11 to 13 degrees even. And then summer and fall follow the same patterns, but the legend here is a little inflated, especially under the high emissions scenarios. So here that same color really looks at temperatures that are increasing from 14 to 16 degrees Fahrenheit. So those summer temperatures are really cooking. And under the same models and emissions scenarios, we can look at precipitation projections as well. And precipitation always shows a little more variation. And so that's definitely true for West Virginia. Under the low emissions, we can expect an increase of 4 to 6 inches over most of the region. But then these darker colored pockets see increases of 6 to 8 inches. And then under the low emissions scenario, we see an increase in precipitation as well, but it's more moderate. So it's up to 2 to 4 inches, or maybe a little more in the eastern part of the state. And exactly when this precipitation comes is very important for ecosystems, whether this precipitation comes in the summer or the winter. So here we're looking at winter and spring. Winter sees increases in precipitation under both scenarios, while spring might increase under the high emission scenario, but then change very little or even decrease under the low emission scenario. And in summer and fall, we can see increases under the low scenario, those yellow colors, and then, I'm sorry, in summer and fall, we see increases under the low scenario, the blue colors, and then see possible decreases in precipitation under the high scenario, which is these yellow colors in summer and fall. And downscaled daily climate data can also be used to estimate the frequency of extreme high temperatures and low temperatures. So under a low emissions scenario, West Virginia is projected to have at least 15 more days per year with a maximum temperature that's over 90 degrees Fahrenheit. And under a high emissions scenario, extremely hot days are projected to increase by 16 to 60 more days per year. And as this map shows, the temperature on those hot days will be even hotter by a couple of degrees under the low emissions scenario to more than 9 degrees under the high emissions scenario. And this increase in hot days is also expected to increase the frequency of heat waves that are lasting 3 days or more. And then on the flip side, temperatures on our coldest days are also expected to warm up and not dip quite so low, resulting in very fewer very cold days where temperature dips below 32 degrees Fahrenheit. And these changes in temperature and precipitation are expected to have wide-ranging effects on tree species in West Virginia. So next, I'll cover 7 ways in which these changes in temperature and precipitation are likely to interact with different physical and biological processes that are important to forest ecosystems. And this information was gathered from different important resources like the National Climate Assessment, the Central Appalachians Vulnerability Assessment, different NOAA products, and other published scientific literature. And as we examine each of these impacts, it's important to keep in mind that they will have very different effects on different forest types. For example, if we're thinking about changes in precipitation, a high elevation red spruce system might face different impacts or stresses from a change in precipitation than a dry oak and pine system might. So the first impact is the length of the growing season, which is defined here as the number of days between the last spring freeze and the first autumn freeze. Warmer average temperatures in every season has already resulted in a longer growing season in West Virginia. So we're already seeing spring occurring later by about a week. Spring is occurring earlier by about a week, and then fall is arriving a week later. And then at the end of the century, these models, as shown in these maps, project 21 to 35 more days in the growing season in West Virginia. That's under the low climate scenario. And then under the harsher climate scenario, we're looking at 42 to 50 more days in the growing season. So that's roughly 3 to 7 more weeks in our growing season. And there is evidence worldwide as well as regionally that these increases in growing season length during the past century are partially responsible for observed increases in forest growth and carbon sequestration. However, longer growing seasons can also result in false spring when warmer temperatures cue plants to form early buds and start sap flowing through the tree. So when these processes are followed by a rapid cold snap or an extreme dip in temperature, these newly formed buds or flowers or even the tree itself are at increased risk of frost damage. And snowfall totals are projected to decrease by 30 to 50% under the low scenario and by 50 to 70% under the high scenario. And that's just looking at West Virginia. So with these warmer average temperatures, the snow is expected to melt faster after a snowfall. So this map shows the change in the number of days with snowpack over the eastern US. So in western West Virginia, we see that orange color, which is 15 to 30 fewer days per year, while this eastern West Virginia, this pink color represents about 30 to 60 fewer days per year with snowpack. And with less snowfall and warmer temperatures, snow is less likely to stick around for the winter. So snow cover typically insulates forest soils. So reduced snowpack could leave the soil surface more exposed to fluctuations in air temperature, which is, likely to influence impacts related to soil temperature, water infiltration, and even spring photosynthesis. Soil frost is often considered problematic, and the heaving associated with it can have adverse effects as well, such as uplifting planted seedlings. However, there could also be benefits of frozen soil. For example, it can improve accessibility and minimize disturbance during logging operations. It can also have a profound effect on ecosystem processes by damaging fine roots and altering litter decomposition, nutrient leaching, and measurements of trace gases. Winter snow cover is also an important factor for regulating stream flow throughout much of the year. So as the amount of snowfall decreases, precipitation is expected to come more often in the form of rain. And this change is expected to alter several hydrologic variables, which another presentation we'll get into in much more detail later today. But for example, warmer conditions can accelerate rainfall and runoff and shift peak stream flows earlier so that these streams peak higher in the winter and lower in the spring, ultimately resulting in up to 50% reduction in summer stream flows. Increased winter rain can also increase flashiness and periods of high flows, making areas that are susceptible to culvert washouts and road damage at even higher risk. So then these longer and warmer growing seasons may also lead to increased risk of moisture stress, especially later in the growing season. And it might seem contradictory to expect both an increase in precipitation and an increase in drought in the same year, but timing really is everything. And changes to the hydrologic cycle in the winter and spring can really contribute to worsening conditions in the summer and fall. So in winter and spring, we see earlier peak runoff, but we're also seeing fewer rain events overall, with more rain coming down in a single event. So it's contributing to more storm runoff rather than renewing the soil water. And then summer temperatures are expected to warm even more than winter temperatures, causing more moisture to be lost through evaporation and transpiration. And transpiration, or the loss of water from leaves, is projected to increase due to an increase in the vapor pressure deficit. So this is the phenomenon by which warm air can hold more water and essentially draws water from plant tissues in order to meet the deficit in air water vapor. And this is not so much an issue in cooler air temperatures because there's simply less of that transpiration from plants. Warmer temperatures and variability in precipitation will likely result in stress or even mortality to trees on sites that are already drought prone, or trees with greater moisture requirements, sites that are exposed to the elements, or sites that are overstocked. And CO2 fertilization could potentially be a silver lining in all of this. So as more carbon dioxide is released into the atmosphere, plants are able to increase photosynthesis and increase their water use efficiency in the process. So this diagram shows the stomatal pore in a plant leaf where CO2 enters and water exits. So as more CO2 enters, the opening of the pore gets smaller, reducing the amount of water that is lost to the transpiration. So a very, very cool feature. Although this would be great in an ideal world where trees could take in more CO2 and make more oxygen using less water, there's some limitations that have been identified in research on this topic. So there seems to be limited sink strength, meaning that trees acclimated to increased growth and more CO2 will not equal more growth consistently over time. Additionally, the ability of trees to capitalize on CO2 will vary by species, even individuals, but also by site quality. And then any potential increase in productivity may be offset by drought stress or other disturbances. So it's really a game of balancing to take advantage of this effect. And then tree species will respond uniquely to changes in temperature and precipitation in other ways. So one useful resource for understanding tree species responses is the Climate Change Tree Atlas, developed by Lewis Iverson at the Forest Service's Northern Research Station. So the Tree Atlas uses statistical relationships between forest inventory data, soils, topography, and climate to model current and projected changes in suitable habitat for eastern tree species. So this particular map of black cherry shows a species that is projected to lose suitable habitat through the end of the century. So the map on the left here was taken from the Tree Atlas website, and it shows current suitable habitat. So the areas in green and blue that we see here have the most high quality suitable habitat. So these importance values are higher. And then those areas of yellow are where this darker yellow color is where the species has habitat, but it is of lower importance or perhaps lower quality. So on the right, then, we can see how the habitat may change under two climate scenarios. So under less warming, as shown in the top right, we start to see slightly more yellow and less green. So if we look at West Virginia here, we're really losing that green color, indicating a slight decline in suitable habitat. Not a complete loss, but it's becoming less widespread across West Virginia. And then in the bottom right, under even more warming, we see a significant loss of black cherry habitat. Again, it's not gone completely, but it's expected to become a much less important species on the landscape. And perhaps where black cherry has good quality, high quality habitat now might be the places where you can retain habitat for black cherry through the end of the century. And here is another species, southern red oak, which is currently absent from West Virginia. And I say absent in regards to what the FIA data picked up. So you might even know of pockets where southern red oak currently occupies habitat in West Virginia, but southern red oak is outside the species historic range in most of West Virginia. However, under the low emissions scenario, we start to see some of that habitat creep up through Virginia and West Virginia. And then under the high emissions scenario, we see that range expansion extends even farther north into New England. So that's a species that we could potentially get to know a little bit better and keep an eye on as we continue managing our forests. And from the Climate Change Tree Atlas, we created handouts that summarize species responses in the Central Appalachians region, and then also 3 subregions in West Virginia. So if you're looking at any one of these 3 subregions, we have handouts just like this one that you can find online, and it gives you a more specific set of tree atlas model results for that region. But to make things easy on us today, I'm showing you the newest data for the Central Appalachians. And so the version 4 of the Climate Change Tree Atlas just came out, and there's a couple of new metrics with this newest version. Capability is a new metric that describes the capability of the species to cope with the changing climate. And it's based on the species' current abundance, its projected habitat change class, and also its adaptability score. And then when species respond the same way under both climate scenarios, we have more confidence in those future projections. And so these species with good climate change capability under both scenarios include some of West Virginia's most common tree species. So good habitat for red maple, sugar maple, yellow poplar, northern red oak, chestnut oak, white oak. And unfortunately, there's also some important species that are expected to do poorly under both scenarios. And these include those cold-loving species, basswood, white pine, hemlock, red spruce, aspen, and others. So in general, we can think of our oaks and hickories and pines doing well under climate change, while our cold-loving species are expected to do not so well. And then we also have migration potential built into the new version of the Tree Atlas. And so these 5 species were projected to gain new suitable habitat in the Central Appalachians. And they were also rated by the shift model to be able to occupy that new suitable habitat. So we're looking at cherry bark oak, longleaf pine, slash pine, water oak, and winged elm as potential new habitat species. Extreme events such as heavy rain, heat waves, windstorms, and droughts are projected to become more frequent or severe as a result of climate change. And these disturbances are not built into the Climate Change Tree Atlas. They are typically distinct from the long-term climate averages, and they're especially hard to model. However, they're already becoming challenges in land management, and the impacts of these extreme events is going to be directly tied to the ability of a species or ecosystem to tolerate changes in habitat or a changing disturbance regime. Non-native invasive species are already a major threat to many forests in West Virginia, and I know you're well aware of what you've got already. Many invasive species, unfortunately, will benefit from climate change. This is due to their broad habitat requirements, their ability to leaf out earlier, and their ability to aggressively colonize new areas, especially those that have been disturbed. So warmer temperatures, earlier springs, reduced snowpack, these are all positive for invasive plant species, as is those increases in CO2 that we talked about, which can have positive effects on plant growth. Some of which are pretty savvy at getting to moisture before those native plant species. And then risk is especially high in areas where invasives are established nearby and potentially in systems that are already struggling under one stress or another. And it's clear that there are many direct and indirect effects of climate change. And these interactions between different threats or stressors can shift or amplify ecosystem processes in expected ways, such as when drought increases the susceptibility of a tree to a pest or pathogen, so like drought and oak wilt, but also in unexpected ways that we haven't anticipated yet. And so we really need to keep an eye on these ecosystem processes because interactions may make all the difference. So in the vulnerability assessment, we first identified 9 of the most common or important forest ecosystems in the Central Appalachians. We limited it to 9 simply because as an expert panel, that is essentially all we had the capacity to rate. And so we did some significant lumping of forest systems. And at the workshop, we combined local information about those forest types. We looked at the forest impact models, projected changes to biological and physical processes, and we used all of that information in an expert elicitation process to rate each ecosystem on its vulnerability. And so when we talk about vulnerability, we talk about the function of a system's likely impacts, which can be positive or negative on the system, as well as its adaptive capacity. So that system's ability to naturally overcome those impacts or even take advantage of the new conditions. And so we can see on this chart, if we have, positive potential impacts and high adaptive capacity, then that's a good thing and we'll have low climate change vulnerability. However, if we have very negative potential impacts, as well as a low adaptive capacity, that means that that system is very exposed and not able to handle those climate change impacts very well. And so we'll have high vulnerability to climate change. So of the 9 forest ecosystems that we had the capacity to rate, we can see that we range from low vulnerability to high vulnerability, with our beloved Spruce-Fir and hemlock northern hardwood forests rating highly vulnerable, while the Dry-Mesic and pine oak systems were rated as lower vulnerability. And I think we have a few minutes to cover just a couple of these ratings now. So if we look at the vulnerability of a Spruce-Fir system, which is rated as high vulnerability, this forest ecosystem is a relic from the last ice age. It's geographically distinct in the region, and it's limited to the coolest and wettest habitat in the highest elevations. Red spruce, balsam fir, and other cold adapted species are projected to have large declines in habitat, largely due to increasing temperatures and due to their isolation at the highest elevations. That habitat really isn't shifting northward. It can only shift upward. And so it's really limited by the topography. Decreases in precipitation later in the growing season may also decrease the amount of atmospheric moisture that would otherwise develop into fog in summer or snow in winter, which is how these systems get a boost in moisture. And so if they're not getting that moisture, it can result in drier soil conditions, which would significantly stress this system. And drier conditions could also increase the risk of duff fire in these systems, which this system would not tolerate. And so its adaptive capacity was rated pretty low, while its negative impacts were rated pretty high, which is how it got its high vulnerability rating. Similarly, northern hardwoods, the hemlock northern hardwoods was rated with high vulnerability. And this system is more widespread. It really extends from like southeastern Ohio to those higher elevation mountains of Maryland and West Virginia. So on soils which tend to be less acidic, we can see sugar maple, basswood, beech, ash, along with lesser amounts maybe of black cherry, birch, red maple, tulip tree. And then on those more acidic sites, we usually see mixes of yellow birch, beech, black cherry, red maple, and eastern hemlock. And here the expert panel considered, again, it's those increases in temperature and potential decreases in precipitation that are likely to be most threatening to this moisture-loving system. And the models also projected that many of these dominant species might remain stable under the low emission scenario, but lose suitable habitat, growth potential, under the high emissions scenario. And there was also evidence that changes in temperature and precipitation would alter drought frequency, which would drive pest and disease outbreaks that are common in this system. And also intense rain may increase the disturbance regime. So although this system supports a relatively higher number of tree species and occurs over a wider range of habitats, it was still limited to the cooler and moister end of the kind of the range of microhabitats. Also, the combined effects of acid deposition, drought, and defoliation have already resulted in lower species diversity and reduced adaptive capacity. And where hemlock occurs in this system, its loss would be a critical blow to the identity of this system. So that was one reason it was rated as high vulnerability. And I see I'm running out of time and want to leave a minute or two for questions if you have them. So I won't go too into detail, but the Dry-Mesic oak forest was a system that was rated as low moderate vulnerability. And this was largely because the system is often, stunted and wind flagged on exposed southwest slopes, exposed to climate and extreme conditions anyway. And in addition, the oaks that are a part of this system were rated as doing okay in a changing climate. So either not losing a lot of habitat or even gaining some habitat under both emission scenarios. And where you are on the landscape is really going to determine what climate change impacts are most important for the system that you're working in. So we can take these broad climate change trends and then really step it down to the site level and think about what makes our particular forest stand more or less vulnerable to climate change because of the species that are living there, or the moisture regime, or the soil types, or past disturbance processes. And if you would like any more information about the vulnerability assessment or any of the resources that Maddie mentioned, you can find more information at forestadaptation.org. And my email address is pleopold@mtu.edu. So email me if you need more information or need to get me your SAF certification number so that you can get credit.